Here are the answers for the section 4-6 homework. We're going to find greatest common factor and least common multiple of polynomials. This skill is related to what we did in section 4-3. We found GCF and LCM of monomials. The way that we did it was to factor each of the monomials, and then by looking at the factors, we were able to figure out which ones were in common, as well as use those factors to find the least common multiple. Let's use the same technique for polynomials. So factor it. In number 1, this binomial factors. There's a greatest common factor of 2. And then the other factor is t plus 3. This one over here can just stay as t plus 3. Let's do question A first and find the greatest common factor. Is the factor 2 in both of the expressions? No, it's not. Is the factor t plus 3 in both of the expressions? Yes, it is. So our greatest common factor has the t plus 3. Now let's do question B and build the least common multiple. From the first expression, we need to choose the factor of 2. Let's put that in our LCM. And we need to choose the factor t plus 3. Let's put that in our LCM. Now go to the other expression. Have we already included a t plus 3? Yes, we have. So this is our LCM. If we multiply these back together with the distributive property, we'll have our LCM written as a binomial. It is 2t plus 6. For number 3, let's use that same technique to find question A, the greatest common factor, and then question B, the least common multiple. We want to have factored form, so we need to factor this difference of squares. S plus 5 times S minus 5. Over here, there's a greatest common factor of 2. 2 times S plus 5. Let's find our greatest common factor for both of these. Is there an S plus 5 in both of them? That's common, so let's write S plus 5. Is there an S minus 5 factor in both of them? Nope, there's not one of those over here. Is there a 2 in both of them? Nope, no 2's over here. So our greatest common factor is only S plus 5. What we're saying is that this expression will divide by S plus 5, and this one over here will also divide by S plus 5. Now let's create our least common multiple. From the first expression, choose the first factor you see, S plus 5. Then choose the other factor you see, the S minus 5. I need to put S plus 5 in parentheses so that when I write S minus 5 next to it, it looks correct. Now go to the other expression. Have we yet included a 2? Nope. So include a 2 in your LCM. You can put it here on the end, or anticipating later that it would be better to have the 2 in front, we can put the 2 out front. Have we already included an S plus 5? Yep, here it is already. Now we can multiply this back together to get this in standard form. Remember that S plus 5 times S minus 5 makes S squared minus 25. Then we can distribute the 2. We get 2s squared minus 50. That's our least common multiple. This first expression can be changed into that multiple by multiplying it by 2. The other expression can be changed into that multiple by multiplying it by S minus 5. For question 5, we have 3 expressions, and they're already all in factored form. Although if it helps you, you can write it in expanded form. This one's x times x, and this one over here is -1 times x times x times x. You don't have to write expanded form. Only do that if it helps you find the GCF and the LCM. Okay, let's get our greatest common factor first. Is there a factor of x common to all of them? Yes, there is. So the greatest common factor is a single x. The other expressions have more than one x, but because the first one only has that one x, that's all we can have in the greatest common factor. Question B, let's create the least common multiple. We need to have an x. Now go to the next expression. We already have one x, but we don't yet have the second x, so let's add that in there. And now go to the third one. We already have a pair of x's, but we don't yet have the third x. So put another one of those on there. This is really x to the third power. What we're saying is that x to the third power is a multiple of x. You would have to multiply x by x squared to make an x to the third. We're saying that x to the third is a multiple of x squared. You'd have to multiply by an x to make an x cubed. And we're saying that x to the third is a multiple of this one. You'd have to multiply it by -1 to make x cubed. Number 7. This first one is already in factored form, and the second one is already in factored form. So let's find our greatest common factor and our least common multiple. What is the GCF of 48 and 16? What is the greatest factor that divides into them? They both divide by 16. Now let's look at the variable y. This one has y squared. Does the other one have at least y squared? Yup, it has more than enough y's to have y squared as a GCF. So include y squared in our GCF. Now look at y plus 2. Is there a y plus 2 in the other expression? Nope. Now look at y minus 3. In the other expression, is there a factor y minus 3? Yes, there is. So include y minus 3 in our greatest common factor. Now we can use the distributive property to make standard form. This is 16y cubed minus 48y squared. Now our least common multiple. We're going to build that from the factors in these numbers. What is the least common multiple of a 48 and a 32? The first multiple of 48 is 48 itself, but 48 is not a multiple of 32. The second multiple of 48 is 96, because 48 times 2 is 96. Is 96 a multiple of 32? Yes, it is. 32 times 3 is 96. So the least multiple that's common for 48 and 32 is the number 96. Now let's look at the variable y. This one has y squared. The other has y cubed. The least common multiple is y cubed. Y cubed is a multiple of y squared. You just need to times it by y to make y cubed. Now we need a factor of y plus 2. And now we need a factor of y minus 3 squared. When we look at the other expression, make sure that we haven't neglected any factors. We already used 96 as the LCM of 32. We already have our y to the third power, and we already have included a y minus 3. Here is our least common multiple. This time I'm not going to expand this out because that would involve too much algebra. Number 9, we have 3 expressions. This one's already factored, this one's already factored, and this one here can be factored. Both terms divide by 6y. 6y times 1 makes 6y, and 6y times negative y squared makes the 6y cubed. This is a difference of squares, so it factors farther. 2 sets of parentheses, 1 plus y, 1 minus y. Now let's get question A and question B answered. Let's make our greatest common factor. Do all of them have a y in it? So the greatest common factor is y. There's not going to be anything else in the greatest common factor because our first expression only has a y. So how can it divide by anything else? Now let's make the LCM. From the first expression, we know it's got to have a y in it. From the second expression, we know it's got to have a 3 in it. And we see that we don't have enough y's written down. We really want to have y to the third power, not just a single y. Now to the third expression. We see that we want our coefficient to be a 6, not a 3. So let's change that to a 6 out front. Have we already included a y? Yes, we have. Have we included the 1 plus y or the 1 minus y? Nope, we're missing those. So let's put those on our LCM also. So our answer is 6y cubed times 1 plus y times 1 minus y. Again, I'm going to leave that in factored form instead of multiplying it out. Number 11, let's factor these expressions. The first one divides by 6x, leaving x minus 1. This one over here has a GCF of 4, so let's factor out a 4. Now let's factor the trinomial using FOIL. X times x is x squared. Negative 5 times negative 1 makes positive 5, and the negative 5 plus the negative 1 combine to the negative 6. Let's do question A and question B. Okay, our greatest common factor. What is the greatest number that's a factor of 6 and it's a factor of 4? The highest number you can think of that divides into 6 and into 4. It's 2. Is there an x common to both of them? No, there's not. Is there an x minus 1 common to both of them? Yes, there is. So our GCF is 2 times x minus 1. We can leave it like this or distribute. Okay, question B, let's make our LCM. Start with your numerical coefficient. What is the least common multiple of 6 and 4? The first multiple of 6 is 6 itself. Is 6 a multiple of 4? Nope. The second multiple of 6 would be 6 times 2, which is 12. Is 12 a multiple of 4? Yes, it is. So in our LCM, we want to begin with 12. Now we see that we have to have a factor of x. And we see that we need to have a factor of x minus 1. Now go to the other expression. Are there any factors we haven't yet included in our LCM? We don't yet have the x minus 5. Here is our LCM. I'm going to leave it in that form. Number 13, let's factor these polynomials. The first one has a GCF of t to the third. That leaves t plus 1. The second one has a GCF of t to the fifth. And that leaves t squared minus 1. T squared minus 1 is a difference of squares. So this makes t to the fifth times t plus 1 times t minus 1. Now let's do question A and question B. The greatest common factor. What is the greatest amount of t's that will divide into t to the third? It's t to the third. There's enough t's to divide by t to the third. Does this one have enough t's to divide by t to the third? Yes, it does. So our GCF has t to the third. Now, is t plus 1 a common factor? Yes, it is. So write down t plus 1. We can leave it like this or distribute. Question B, let's make our LCM. From the first expression, we have t to the third, but in the other one, we see we have more t's. So we need to have t to the fifth in our least common multiple. We see that t plus 1 is common to both, so let's include that in our common multiple. And finally, we see that this expression has a t minus 1. We need to include it in our common multiple. Here is the least common multiple of both expressions. This first one could be changed into that if you multiply by t squared and t minus 1. The other one, however, doesn't need to be multiplied by anything to make that least common multiple. For the review, we're going back to page 138 where we are practicing all of our factoring patterns. So number 22, look for a greatest common factor, but there isn't one. Look to see if it's a special pattern. It's not a perfect square trinomial. So let's try factoring using FOIL. M times m is your m squared. Now what times what is negative 360 n squared? Both of them will need an n. Now let's put some thought into making negative 360. There's lots of possibilities. Because it's negative 360, one of our numbers must be positive and one of our numbers must be negative. One possibility would be 36 times negative 10. But when you combine these together, that makes 26, and that is not what's in the middle. So let's find another pair of numbers that multiply to negative 360. Positive 20 times negative 18 is negative 360. And 20 plus negative 18 is 2, and that is what the middle term is. So we know we need to have positive 20 and minus 18. Number 24 does not have a greatest common factor, and it is not a perfect square trinomial. It can't be a perfect square trinomial if this is negative. Let's try FOIL. N times n is your n squared. What times what is negative 420r squared? They both have to have an r in them. Now let's work on getting the negative 420. One possibility is 42 times negative 10. But these add together to make 32, and that is not what's in the middle. Let's find another pair of numbers that multiply to negative 420. 21 times negative 20 is negative 420. But these add together to make 1. That's not the right amount either. We want to make 23. Let's find another pair of numbers on our calculator. By experimenting with different numbers on the calculator, I'm able to find that 35 times negative 12 is negative 420. And 35 plus negative 12 is 23. So we need positive 35 and a minus 12. Number 26. All of the coefficients are even numbers, so there's going to be a greatest common factor. Is it a 2, is it a 4, or is it an 8? Let's use a calculator and see if 1440 does divide by 8 evenly. And it does. It makes 180. So we can factor a GCF of 8 out the front. 8 times x squared is 8x squared. 8 times negative 3x is negative 24x. And 8 times negative 180 is the negative 1440. Now let's factor this trinomial using FOIL. X times x is our x squared. Now what times what makes negative 80? One possibility is negative 18 times 10. But this combines to negative 8. And we want to combine to minus 3. Let's find another pair of numbers that are only 3 units apart instead of 8 units apart. With the calculator's help, we can find out that negative 15 times positive 12 is negative 180. And negative 15 plus 12 does combine to negative 3, which is our middle coefficient. So we need negative 15 and positive 12. Number 28, there's no greatest common factor. Let's try factoring using FOIL. To make x to the 4th power, we need x squared times x squared. Now let's find two numbers that multiply to negative 40. And looking in the middle, we want our two numbers to be 3 units apart. How about going with negative 8 times positive 5? These two add up to negative 3. So we want to put minus 8 and plus 5. On page 135, we're continuing with factoring. This binomial is a difference, so we want to know if it's one of our special patterns, a difference of squares or a difference of cubes. I see the 3rd power, so I'm thinking it's a difference of cubes. The cube root of 216 is 6, and the cube root of z cubed is z. The parenthesis pattern is a small set followed by a longer set. Fill in the 6 in the z and choose the same sign that you have in the middle, a minus. Now square the 6. Change to plus. Take the product of the two things. Put plus again and square the z. Number 30. This is a binomial. Is it a difference? No minus sign. Is it a sum of cubes? Can you take the cube root of x to the 6th and get a nice answer? You can. You get x squared. And the cube root of 125 is 5. So let's put our parentheses and then fill them in. Here's the x squared plus 5. Now square the x squared. We get x to the 4th. Switch to minus. Take the product of those two things. We get 5x squared. Put a plus and square the 5. Number 41 has 4 terms. So I'm thinking grouping. If I group just the first two together, I can factor out a y, and I get y times y plus 2. But when I group these together and factor it, I'm not going to have anything that matches either the y or the y plus 2. So grouping in that way will not get me a common factor. So let's group it as a trinomial followed by the monomial. Can this trinomial be factored? Yes, it can. It is a perfect square trinomial. It makes one set of parentheses squared with y plus 1 inside of there. Then let's write down the minus in the 9t squared. Look at this polynomial. This is a binomial. It has its first term, it has the second term, it's got the minus between them. This is a difference. Is this difference one of our special patterns? It is. It is a difference of squares. I know that because this is something squared. This over here is something squared. This is a difference of squares. So put the parenthesis pattern that you use for difference of squares. Y plus 1 times y plus 1 is the y plus 1 to the second power. Positive 3t times negative 3t is the negative 9t squared. So here is our factored form. We used grouping, but we grouped it as a trinomial and a monomial. Number 42 has 4 terms, so I'm automatically thinking about grouping. If we group just the first two together, there is a GCF of 4a, and that would leave a minus b. But how are you going to factor this thing so it has anything with a's in it so that you get something in common? You can't. So grouping it like that is not going to accomplish anything. Let's group it in a different way. The first thing I'm going to do is rearrange the terms so that it looks like this. Now group the trinomial and separately keep the monomial. This trinomial is a special pattern. It is a perfect square trinomial. One set of parentheses squared. 2a minus b. Then keep your minus 36. This polynomial has 2 terms. Here's the first one, here's the other one, and it's a minus, so it is a difference. Is it a difference of squares? Yes, it is. So 2 sets of parentheses, 2a minus b and 2a minus b. And then how about to make negative 36? We need positive 6 and negative 6. For page 132, we were prime factoring. We were taking numbers and breaking them down into their component prime number factors. A systematic way is to divide by primes. This ends in 5, so I know for sure it divides by 5. Take your calculator and type 2475 divide by 5. We can rewrite this as 5 times 495. Well, 495 ends in 5, so we know it can be divided by 5. Take a calculator and go 495 divide by 5. And that makes 99. So far we have 5 times 99. Can 99 be divided by any prime numbers? 99 divides by 3. So we have 5 times 5 times 3 times 33. Can 33 be divided by any primes? Yup, 33 divides by 3. So we have 5 times 5 times 3 times 3 times 11. Here's our prime factorization, although it's more common to write using exponents. For number 8, we have the number 67. Let's try dividing by primes. It won't divide by 2, it's not even. It won't divide evenly by 3. It won't divide evenly by 5. It won't divide evenly by 7, or 11, or 13. Now you can keep trying more primes, but I think you'll find out it doesn't divide by anything. So this one is already prime.